Good morning. We are cadets Alexander Przekora,
Silas Wilson,
and Minchan Kim.
and our project for SCUDEM Problem C is Birds of Different Feathers. We are coached by Major Colgan. The core question posed by SCUDEM is whether mixed species groups are more effective at detecting predators than single species groups. We were asked to provide mathematical evidence for this advantage and to consider the impact of the number of species involved, including potential minimum or upper bounds. To build a model, we first needed a real-world case study. We chose the well-documented symbiotic relationship between zebra and wildebeest. These two species group together to compensate for each other's weaknesses. By modeling this two-prey, one-predator system, we can build a foundational model to answer the problem. We plan to use data from aerial and experimental AI-powered satellite surveys of the Great Migration. I will now pass this further on to Cadet Wilson to explain our mathematical framework.
Thank you, Alex. To build our model, we first defined our variables. We have three dependent variables: the population of wildebeest, W of t, zebra, Z of t, and predators, P of t, all as a function of time, t, and days. We established three key assumptions to simplify the model. First, population loss is only from predator encounters. We are not factoring in disease or exhaustion. Second, no births occur during the 120-day migration. And third, every predator encounter results in a kill. We do not account for prey survival, such as if a wildebeest or zebra were to put up a fight against a lion. Our core methodology is a three-species Lotka-Volterra, also known as predator-prey model. The first two equations show the prey populations of zebra and wildebeest growing naturally but decreasing based on encounters with predators. The third equation shows the predator population decreasing from natural death but gaining energy or growing from successful encounters with both zebras and wildebeest in which they kill the prey. This model alone does not answer the question. We needed to prove that grouping itself provides an advantage. To do this, we used a Kolmogorov Mutualism Index, or M. This index compares the predator attack rates, beta, in two different scenarios. First, the pairwise rate, which is the attack rate on zebras alone and wildebeest alone. Second, the combined rate, which is the attack rate when both zebras and wildebeest are together. If M is close to 1, it confirms a strong beneficial relationship. Cadet Kim will now show our results from this calculation.
Thank you, Silas. We fitted our Lotka-Volterra model to migration data to find these predation coefficients. First, we were able to calculate the average pairwise attack rate, which came out to be 4.89 times 10 to the negative 5th. Secondly, we found the average combined attack rate, which was 2.61 times 10 to the negative 6. As you can see, this predation coefficient is an order of magnitude lower when the species are combined, which is a significant finding. Plugging these values into the Kolmogorov equation gave us a mutualism index of M equals 0.947. This result, being very close to 1, gives us our first major finding. There exists a strong, quantifiable, positive mutualistic relationship between these two species. Next, we had to connect this M value to the probability of an encounter. In order to do this, we utilized a Poisson distribution. This Poisson distribution will model the probability of k events happening over a fixed interval of time. We defined the mean encounter rate, lambda, as a function of our mutualism index, which you can see from this equation, lambda equals initial 1 plus m. The graph on the right visualizes this encounter. As you can see, it shows a clear, distinct linear relationship. As the mutualism index M increases, the predator encounter rate fluctuates. This directly links the species cooperation to the predator attack, where a higher cooperation has resulted in a lower predator attack rate. Now, with the determined N value of 0.947, we calculated a new encounter rate of 0.1947 events per day. Now, since this migration happened over a 120-day interval, this would mean that we would have to multiply this value by 120 to give us an expected mean of 23.364 predator encounters. Now, the graph here depicts a Poisson distribution where the bars show the probability of exactly k encounters, with the most likely number being 23. The line shows the cumulative probability, which helps us answer questions like, what is the probability of 30 or fewer encounters? In conclusion, our model provides quantitative evidence to answer the SCUDEM problem. First, we're able to answer the question, is there an advantage? Yes. The mutualism index of 0.947 proves the combined group is safer and more effective at migrating from predation in comparison to when they would work individually as a species. We're able to answer a second question. What does this mean? It means that over the migration, the herd will experience a mean of 23 predator events. As our proposal notes, this indicates they are surviving more than they should normally be. For future references, this two-species models can be expanded to 3 or more species to attribute for confounding variables or to find upper bounds of this advantage. Thank you. This concludes our briefing.